In this video, we'll take a look at excitation tables. If we know what state we want to go to in our next state table, the excitation table helps us figure out what flip-flop inputs will excite that to happen. If we choose a D flip-flop, the next state is the the next state equation is the D flip-flop equation, but that's not necessarily true for other flip-flops, for the JK flip-flop and the T flip-flop. So this excitation table will help us get from the next state equation for each state variable to the flip-flop input equations. We can derive the excitation table from the characteristic table for a flip-flop. So if we take a look here at our JK flip-flop, for example, if we know the possibilities for present state to next state, present state 0, 0, present state 0 to 1, or present state is 1 goes to 0, or 1 goes to 1. So this is the excitation table because the input side is all the different possibilities. This is what the JK inputs we could be set to. So if our present state is 0 and our next state is 0, well, that could be stay the same, right? So that could be same here, 0 to 0, or it could be to just, we're going to 0, so we could just reset it. So it's, or it could be reset. So we have either of those two options, 0, 0 or 0, 1. So J has to be 0, but K could be either 0 or 1, and we'd still get the next state to go to 0 as we want. So if our present state is 0 and we want to go to 1, well, we could do that by setting here, or we could do that by toggling. So this is either a set, so I'll do set comma toggle are our two options. So set and toggle, our J has to be a 1, but again our K could be either 0 or 1, and that would be do either set or toggle. Thirdly, here we have if our present state is 1 and we want to go to state 0, that could be a reset or it could be a toggle. So reset and toggle, K is 1 in both situations, so our K must be a 1, but our J could be a 0 or a 1, so that's an X. So this is reset. Or toggle, and then at 1 to 1, that's set or same. So that's set or same, and if we look up here at set or same, same is 0, 0, set is 1, 0, so K has to be a 0 and J could be either. So this is our excitation table when we have this scenario. So having these don't care conditions for K or J will simplify the combinational logic in front of the flip-flop in order to whatever combinationally determine what that flip-flop input will be. So that's how we can derive the excitation table. If we're not given the excitation table, we can derive it from the characteristic table of the JK flip-flop. And then we learned how to derive the characteristic table of the JK flip-flop in past videos. So for a toggle flip-flop, that's just a little bit easier because you either toggle or don't toggle. So from 0 to 0, we don't toggle. So our toggle flip-flop only has these two actions. It doesn't have a set or reset action. So this is just same. This is toggle. This is same. And this is, oops, sorry, that's toggle. That's toggle. And this is same. So these are our excitation tables. So let's take a look at solving a problem using these excitation tables. So the JK is a little bit more complicated to use. So we'll look at that example first. And here we have a transition table or a next state table. We have two state variables, A and B. So our present state of A and B. The first two rows, our present state is 0. Second two rows, our present state is 1. Third two rows, our present state is 2. And our fourth two rows, our present state is 3. And then based on the input changing between 0 and 1. So what we want to look at for these flip-flop input equations, though, if we just look at A, initially, if we just pick our JA and KA, A is going from 0 to 0. So up here, this 0 to 0, what we're going to put up here for A, or JA and KA, are 0 and don't care. And then if we look at the next row here, we go from 0 to 0 again, so that's the same. J must be 0, K is don't care. If we're going from 0 or 1, that's either a set or a toggle. If we look up here, instead of having to figure it out, we can just look up here, and that's a 1, or don't care. And now we're going from, again, now we're going from 0 to 0 again, so that's our same 0, X, and then we go from 1 to 1. 1 to 1 is either a set or same, so that's a, we'll look up here, that's, we don't care about J, but K is a 0. And then we go from 1 to 1 again, don't care about J, K is a 0. We go from 1 to 1 again, we don't care about J, K is a 0. And finally, we go from 1 to 0, so 1, 0 up here, we don't care about J, and K is a 1, so X, 1. So you should probably pause this video and see if you can't fill out the right answers for JB and KB, and then when we come back, you can check your answers. So why don't you pause the video. Okay, I'm assuming you're back now, so hopefully this is what you filled out for JB and KB. For B, we went from 0 to 0. That's a reset, or stay the same. That's 0x. Then we get the 1x, x1, x0, 0x, 1x, x0, x1. So make sure that you can do this instead of just watching the video. Practice while you're doing it. So, but now we have our flip-flop input equations. So what's our next step that we need to do in the synthesis? Remember, what we're going from is from our, originally we had some type of a state diagram. We went to a state table. We skipped the state diagram part. We just started with a state table, used the excitation table to create the flip-flop input equations, and then what we need to do is create a logic diagram. So finally, a logic diagram, we need to get an equation for each of these, a Boolean function for each of these, so we can get our Boolean logic. So we'll put those into a Karnaugh map. And notice how when, so we have our A, B, and X, and remember A, B, and X, those are present states of A and B, not next state of A and B. This JA here and this KA are going to set the next state. So make sure you're using the present state. And we can use this don't care. So we get JA is B X prime. If we don't use this don't care, we might have additional ones in here or zeros, but we use the don't care. It helps minimize our equation. Similarly, BX for our K, and then JB is just X, and KB is, we can write that as A exclusive or X prime, meaning it's A exclusive NORD with X, the not of that. And then we culminate with our logic diagram. And this is a sequential circuit for something that we have looked at in the past, but now we've implemented it with the JK flip-flop. All right, in the next video, we will look at a T flip-flop.